Hi guys, welcome to my kitchen. As promised, I'm going to give you a little lesson on two theorems that are quite important in calculus. One's called the mean value theorem, and the other one is called Rolle's theorem. So I'm going to go through this like I normally would in class, where I'm going to give you an introduction to the theorems. I'll draw you a picture, and then I'm going to go through three examples. I've already written out the examples and the work that goes with them. So I think the smartest way to do this would be for you to grab a notebook, a pen, and to just sort of pretend you're in class. So when I introduce something, you might want to pause this video and write down the theorem, and then when I give you a problem, pause it, do the problem, and then when you think you got it, or if you're stuck, you can play the video to see how I did it. If you have questions about anything that we're doing today, remember you have all class Wednesday to ask me. Alright, first one, here it is. This is called the mean value theorem. So I've drawn you a little picture, so I think it'll help if you draw this. So from now on, I'm going to call this the MVT. But basically, this is a theorem that holds for a function over a closed interval, and the function has to be both continuous and it has to be differentiable. I'm going to write that here in a second. But just as long as the function is continuous and differentiable, you are guaranteed a certain result, which I'm going to write here. So let me write that. So this function has to be continuous over the closed interval a to b, and it has to be differentiable over the same interval but open a to b. Remember that functions are always continuous over the closed and differentiable over the open. So you definitely want to write that down first. Okay, so what this function says, or excuse me, what this theorem says is that if you have a function that satisfies these conditions, you can draw a secant line. So remember, a secant line is just a line that starts at a point and goes through another point. So I could draw a secant line through the function that starts at A and goes through B. So just to remind you what a secant line looks like this. Alright, there you go. So here's a secant line that goes through points A and B. So what this theorem says, and if it doesn't make a whole lot of sense to you, I think what I would do is draw a picture similar to what I did and really convince yourself that no matter what you draw, just as long as this is true, what I'm about to tell you is always going to happen. So the theorem says that no matter what, you will always have a secant line whose slope is equal to some tangent line drawn in your interval. Okay, so what that means is that I can find some number in between A and B. I can draw the tangent line at that point, and I'm guaranteed that there exists at least one point where that line will be parallel to this line. So you can see that I think if I drew this to scale here, that probably happens around I don't know, I think around here-ish. It might happen more than once, but you're guaranteed that it happens at least once. So let's write that down in words. Remember what this says now. It says that you're guaranteed that the slope of the secant line is equal to the slope of some tangent line in your interval. Okay, so let me write that down. Alright, so it looks sort of complicated, but if you break it down into really what it stands for, it's not so much. All this is saying is that there exists a C. Oh, wait, this is really important. Let me start it. Is the existence of this C. You're guaranteed that this lives somewhere on the open interval. It has to be on the open interval. If for some reason you're doing algebra in a little bit and you end up going through this process, which I'll explain in a second, and you get actually one of these values that are on the endpoints, you have to get rid of it. Okay, MVT guarantees the existence of the C somewhere between A and B, but actually not A and B itself. Again, something I think will make sense if you really think about this picture. Okay, so all this is saying is that there exists a C somewhere in your interval, so that the slope of the tangent, well, this is hard backwards, right there, slope of the tangent is equal to the slope of the secant, which is right there. Okay? That's the mean value theorem. So let me give you an example of what a problem will look like, and then we'll go on to Rolle's theorem. Again, after I give the problem, you might want to pause it and actually try it. All right, here you go. Okay, so a classic problem is going to look something like this. Verify that the mean value theorem applies to some function over some interval, and then find all the values of C that satisfy the conclusion of it. Okay, so in a nutshell, what you want to do is sort of informally just convince yourself that the MVT holds. And all that means is convince yourself that this function is both continuous over the interval 1 to 4 and is differentiable over the interval 1 to 4 as well. And rational functions are fine just as long as you're not dealing with a denominator equal to 0. So even though x is equal to when x is equal to -2, your function's not continuous. -2 is not in our interval. Okay, so the MVT works. All this means, remember, if you look back at the conclusion, is that you're going to take the derivative, that's the f prime of c part, and you're going to set it equal to f of b minus f of a over b minus a. You're going to solve that equation and then just write down any solutions you get that are in our interval. That's the key. It has to be between 1 and 4, and it can't equal 1 and it can't equal 4. So if you want to try the problem, I would pause it now and go for it. Okay, welcome back. Here's the answer. Okay, so I started with up here actually finding the slope of the secant line, okay, which was 1/9. I took the derivative using the quotient rule, which simplifies down to here. And then all you do, guys, is you set equal the derivative to the slope of the secant line. So that's right there. Once I have that equation, I solved it. But notice, extreme close up, you end up getting -2 plus or minus 3 square root 2. Only one of those is in your interval. Between 1 and 4, the number that I've circled is the only number in your interval. So what that means is that at that x value, if you were to draw a tangent line to that curve, it would be parallel to the secant line. Okay, in other words, your average rate of change of that function is equal to the instantaneous rate of change when c is equal to -2 plus 3 root 2. All right, mean value theorem. Rolle's theorem is the second theorem I want you guys to think about, and it's really just a consequence of the mean value theorem. So all Rolle's theorem is it applies to a function that looks like this. And the only thing that's different is that we require that f of a and f of b are the same thing. So in other words, this y value and this y value have to be the same thing. So if f of a equals f of b, Rolle's theorem is just a consequence of the mean value theorem. Everything else is the same. So let me write down those now 3 conditions, and maybe it'll make sense what the conclusion is going to be if you think about the difference here. All right, so let me write that down. So for Rolle's theorem, you just need f of a and f of b to be the same. You need the function to still be continuous over the closed and differentiable over the open. So if you actually apply the MVT here, the slope of the secant line is what? Think about it. Well, if f of a equals f of b, and you can see it visually here, the slope of the secant line would be 0. So if all three of these conditions are met, what that guarantees is that the derivative is equal to 0 somewhere between a and b. Okay, so let me write that down. So again, the conclusion is that there exists a c, again, over the open interval. I can't stress that enough. You have to make sure it's in the open interval, so that f prime of c equals 0. Okay, again, please don't overthink this or anything. This is the mean value theorem. It's just, in this case, the slope of the secant line, instead of f of b minus f of a over b minus a, we know that it's 0. Okay, so all this is saying is that you take the derivative, set it equal to 0. Rolle's theorem. It's a good one. Okay, so again, I'm going to give you an example. I think once I put it on the screen, I want you to do it. And then again, once you're done, unpause it and then check. Okay, so the question is going to look awfully similar to the one I just gave you, but now it just says verify Rolle's theorem applies to this function over this interval, and then find all values satisfied by the conclusion of it. Okay, so this one is really nothing more than, again, I don't know, it's still an informal verification, but you have to at least check that f of the two endpoints match. So in this case, they do. F of 0 is 1 and f of 4 is 1. Again, I sort of just did an informal check that it was continuous and differentiable. Okay, Rolle's theorem is wicked easy. It's much less tedious than the mean value theorem. All this says, once you know that it works, is that you take the derivative and then you set it equal to 0. So I did that over here, and I ended up getting that x equals 2. Now I have to check, is 2 in the open interval? Well, it should be, since I'm guaranteed the existence of it. But remember, if you had more than one answer, chances are one of them might not work. So you got to check. Okay, so 2 is certainly in between the open interval 0 to 4, so 2 works. So all that means, guys, is that in this interval, when x is equal to 2, the slope of that tangent line and secant line are both 0. And that makes sense because that would be at this function's vertex. Okay, Rolle's theorem. So I now want to give you a problem that's a little less traditional, one that might be a little bit more challenging for you guys. So I have one here. Again, same idea. Read it, try it, and then I'll give you the answer. So this one is a little bit more indicative of the level we might ask you on a test or a quiz. And it looks something like this. Assume f is continuous over some closed interval and differentiable over the open interval. Okay, that's like clue that use the MVT. Okay. Over this interval, if f of 1 is equal to 10 and f prime of x is always greater than or equal to 2, how small can f of 4 possibly be? Okay, so take a second, try it. All right, so let's go through the solution. So here it is, and I'll explain it. Since the mean value theorem applies, we know the existence of a c that satisfies this line next to my finger here. So I then plugged in some givens. We know f of 1 is 10. We know that the denominator 4 minus 1 simplifies to 3. And we know that the smallest value of our derivative is 2. So I plugged in the corresponding pieces, and I ended up with this equation, or this inequality actually. And once, remember the question asked for f of 4, so once we do some shuffling and we solve for f of 4, we end up getting that f of 4 is always going to be greater than or equal to 16. So the smallest value f of 4 can take would be 16. Alright, hope that helps. I think you're now ready to do the classwork. I really do want you to come into Wednesday having attempted the mean value theorem and Rolle's theorem day, so that Wednesday I will just be able to answer questions, and then Thursday you guys should be all set for your quiz. As always, if you have questions, come see me, come to Math Center, let me know when I can meet with you to help clear things up. Alright, Adios, guys. Peace.